morning. We are TRASH.PY. My name is Marcella, and I'm the design and manufacturing lead.
And I'm Ethan, the computer vision lead.
Did you know that 91% of plastic does not get recycled and just sits in landfills annually? When we learned about this awful statistic, we had to figure out the issue applies to us and what we can do to help. We first sought out some people on campus we believe could provide us resources and guidance to better understand the problem. From these stakeholder conversations we had with the Office of Campus Sustainability, some professors, and sustainability-focused project teams, we were able to develop a broader perspective on the issues on campus, which can be distilled into four main pain points. One, that recycling at the University of Michigan is contaminated. Two, there are many recyclables that could be salvaged. Three, people can't decide where to throw their waste. And four, sometimes the whole system just ends up breaking down.
So we did some research. From data that we were able to obtain from the OCS, we've calculated that 40% of recycling on campus is contaminated. Among these contaminants, we identified that the biggest culprits are coffee cups, plastic bags, unrecyclable paper products, and unacceptable food packaging. But that is only half of our stakeholders. The other half is the users, the students and janitorial staff. We surveyed 59 students, and we learned that only 10% of students feel strongly confident that they can dispose of their waste in the correct receptacles. Furthermore, 62% of respondents say that they will use the other bin if one of the bins is filled to the brim. And finally, 60% say that they would be happy if they were not expected to make any decisions while disposing of their waste. And if that doesn't convince you that the university bins are bad, just look around. One of our team members took this picture just this week at the union. This is a problem.
And this is our solution, TRASH.PY, a system ensuring proper waste sorting and eliminating user decisions. In order to explore the design space for our solution, we started off with large brainstorming sessions as a team to find concepts like the examples shown here. We wanted to make sure that we were able to come up with the best designs possible, but still be creative. From all that we were able to make, we merged our ideas into 10 final ones, which we then used filtering criteria such as ease of use and affinity for taking images to lead us to our final design concept and solution. Our solution then that we decided on has an open latch deposit system that intakes and deposits it into the staging area. In case one, the system concludes that the item thrown in is a recyclable and the right latch swings open to deposit the item in the recycling bin. In case two, the item is trash and the left latch swings opening, depositing it in the trash bin. The solution is also fitted to the existing Michigan bins in order to allow for easier integration and use of items that the university already has available. But how does the sorting system actually work?
Our computer vision system begins by first taking a picture of the waste item that has been deposited. It then uploads that image data to the cloud, where it is received by our AI deep learning model, which classifies the item using a convolutional neural network. The decision data is then sent back to the bin, which can then process the item into the correct receptacle. To test our theories, we built a lo-fi prototype of the staging area and the camera system using the CSED lab. We've also developed a standalone web applet that works with our prototype to help visualize the system working and validate that our model is viable. As you can see, when the classify button is pressed, the system takes an image of the item held in our mock staging area, classifies it as either trash or recycling, and returns the data back to the browser to be displayed. Our current model is trained using the TrashNet dataset, which aims to solve a very similar problem to ours, and the model trained on this data generalizes decently to our example. In the future, we will be making our own data set using actual field data from the machines, which will allow us to be even more accurate. So let's look at the TrashNet data set. It contains over 2,500 images of trash and recycling, labeled by hand and categorized by their material and whether or not they're recyclable. All of the images are taken pretty close up with a white background, which is similar to our use case, although our background isn't flat like theirs. The main difference in the problems being solved with the TrashNet dataset versus ours is that TrashNet aims to additionally classify the type of recycling, so the class sizes of the dataset are balanced accordingly. This results, in our case, in a class imbalanced dataset for TRASH.PY, as we lump all of the recycling categories into one. And this is what our class imbalance looks like. The number of recycling data that we have dwarfs our trash data. Now this is a problem. A model trained on this data set can cheat. A model can ignore the input images entirely and just guess recycling every single time. And during training, it can score a 95% accuracy. To fix this glaring problem, we have employed a technique called random oversampling, or ROS for short, which we achieved by creating additional copies of our trash data and making some small adjustments such as rotation and translation to these images so that we will have an equal number of trash and recycling images that are unique for training.
Some other features in our design come from conversations we had with the janitorial staff. They were a very important aspect of this project. So we don't want to make their job any harder or make any large changes to what they have to do. So therefore, we added a sliding rack in order to give them easy access to changing the bags on the bins. And with using the bins that are already in use, they already have the bags that fit these trash cans. As well, small LED lights on the corner of the bins help signify the status of the bin. Green meaning that everything is working properly, orange indicates that the respective side is full, and red indicates that the machine is not working and needs some sort of maintenance. And in order to sense that the bins are full, the slide out rack has a weight sensor underneath that the bins register when these bins are full. This would then notify the janitorial staff through the TRASH.PY app. This is a basic prototype of how the application would look like. So for each building staff handling the waste, one could choose a required campus and the building to reach their own setup. Each building could have views showing the real-time status of all the bins a staff member is responsible for, along with statistics comparing recyclables versus general waste in these bins. And these are just some basic features that we plan to add more in the future as the system keeps evolving. The current market right now kind of features the Michigan bins as well as two other smart solutions, but Trash.PY is the only solution that meets our criteria of that reduced contamination, reduced decision, a small physical footprint, as well as easy adoption for the University of Michigan. And as we move forward with this project, our main goals include launching the first Trash.PY bin on campus through CSED. CSED has offered to host any prototype we build to gather real world data, which would then be able to help our neural network. As well as we could also want to add compost as a sorting scenario. Michigan emphasizes a lot on compost, and that would be something beneficial to add to it. As well, we want to begin an education campaign in order to inform users about different types of waste and how they can dispose of waste better when they aren't using a Trash.PY bin.